Now, it is true that the temperature difference will have an effect on the rate of heat transfer across the heat transfer surface, as it is clearly shown by the following heat transfer equation, where Q is the heat transferred per unit time, U the overall thermal transmittance, or simply the overall heat transfer coefficient, A the heat transfer area, and delta T the temperature difference between primary and secondary fluid. This equation also shows that the heat transfer will depend on the overall heat transfer coefficient and the heat transfer area. Now, for any single application, the heat transfer area might be fixed. However, the same cannot be said of the U value, and this is the major difference between saturated and superheated steam. The overall U value for superheated steam will vary throughout the process, but will always be much lower than that for saturated steam. It is difficult to predict U values for superheated steam, as these will depend upon many factors. But in general, the higher the degree of superheat, the lower the U value. Typically, for a horizontal steam coil surrounded with water, U values might be as low as 50 to 100 watt per square meter per degree Celsius for superheated steam, but up to 1200 for saturated steam. For steam to oil applications, the U values might be considerably less, perhaps as low as 20 for superheated steam and up to 150 for saturated steam. And in a shell and tube heat exchanger, 100 watt per square meter per degree Celsius for superheated steam versus 500 for saturated steam can be expected. Now, of course, these figures are typical. Actual figures will vary due to other design and operational considerations. Although the temperature of superheated steam is always higher than saturated steam at the same pressure, its ability to transfer heat is therefore much lower. The overall effect is that superheated steam is much less effective at transferring heat than saturated steam at the same pressure. In addition, not only is superheated steam less effective at transferring heat, it is very difficult to quantify it using the heat transfer equation, as the temperature of superheated steam will fall as it gives up its heat while passing along the heating surface. Predicting the size of heat transfer surfaces using superheated steam is difficult and complex. In practice, the basic data needed to perform such calculations is either unknown or empirically obtained, putting their reliability and accuracy in doubt. Clearly, as superheated steam is less effective at transferring heat than saturated steam, then any heating area using superheated steam would have to be larger than a saturated steam coil operating at the same pressure to deliver the same heat flow rate. If there is no choice but to use superheated steam, it is not possible to maintain steam in its superheated state throughout the heating coil or heat exchanger, since as it gives up some of its heat content to the secondary fluid, it cools toward saturation temperature. The amount of heat above saturation is quite small compared with the large amount available as condensation occurs. Ideally, for enhanced heat transfer and optimized heat transfer areas, the superheated steam should reach saturation relatively soon in the process. This allows the steam to condense to produce higher heat transfer rates, result in higher overall U values for the whole coil, and thus reduce the heat transfer area required for the application, which will save considerable costs. If this is so, it is relatively easy and practical to design a heat exchanger with a heating surface area based upon saturated steam at the same pressure, by adding on a certain amount of surface area to allow for the superheat. Using this design guideline, the first part of the heat exchanger will be used purely to reduce the temperature of superheated steam to its saturation point. The rest of the heat exchanger will then be able to take advantage of the higher heat transfer ability of the saturated steam. The effect is that the overall U value may not be much less than if saturated steam were supplied to the heat exchanger. This is depicted in the following example. So, as seen here, less superheat allows the steam to condense in the major part of the coil, thus increasing the overall U value approaching that of saturated steam. Okay, now from practical experience, the extra heating area needed for superheated steam is 1% per 2 degrees Celsius of superheat. This seems to work up to 10 degrees of superheat. We do not recommend that superheated steam above 10 degrees of superheat be used for heating purposes due to the probable disproportionate and uneconomic size of the heating surface, the propensity for fouling by dirt, and the possibility of product spoilage by the high and uneven superheat temperatures. This example is for the sizing of a tube bundle for superheated steam. So let's take a closer look. Superheated steam at 3 bar gauge with 10 degrees of superheat is to be used as the primary heat source for a process heat exchanger with a heating load of 250 kilowatt, heating an oil-based fluid from 80 degrees Celsius to 120 degrees Celsius. Let's estimate the heat exchanger surface area needed for this application. The methodology is as follows. First, consider the heat exchanger if it were heated by saturated steam at the same pressure, so 3 bar gauge. The U value for saturated steam heating oil via a new carbon steel heat exchanger is taken to be 500 watt per square meter per degree Celsius, as highlighted in the bottom table. Now, using the heat transfer equation, we have the following. The heat transfer per unit time is 250,000 watt. The overall heat transfer coefficient 500. The heat transfer area is the parameter to be determined, and delta T is the temperature difference between superheated steam and the oil-based fluid. For the purpose of this example, we will use the arithmetic mean temperature differences to keep the calculation simple. In practice, however, logarithmic mean temperatures would be used for greater accuracy, and this will be explained in detail further ahead. To calculate delta T, we will first assume that the temperature of steam is constant and equal to that of saturated steam at a gauge pressure of 3 bar. According to the saturated steam table, this is equal to 144 degrees Celsius. The temperature of oil will be taken as the arithmetic mean temperature. So, 80 degrees Celsius plus 120 degrees Celsius divided by 2. This gives 100 degrees Celsius. As a result, delta T equals 144 minus 100. This gives 44 degrees Celsius. Now we plug in our variables in the heat transfer equation as seen here. For a result of 11.4 square meters. Therefore, if saturated steam were used, the heating area would be 11.4 square meters. However, in our example, superheated steam is used, with a degree of superheat of 10 degrees Celsius. Now, allowing 1% extra heating area per 2 degrees Celsius of superheat, as it was discussed in the previous video, then the extra amount of the heat exchanger surface area would be 5%. Therefore, the adjusted area for superheated steam would be as follows.